What's up, guys? Uh, we are studying projectile motion, and in the previous lecture, I told you about a special type of projectile motion in which you throw a projectile from a certain height h. In this lecture, we'll be talking about projectile on an inclined plane. Okay, so projectile on an inclined plane. Okay, so this is how it will look like. There's an inclined plane of angle theta, and we are throwing a projectile from the bottom of the inclined plane, and it is striking. So it's not necessary that it strikes the top surface. The inclined plane can be longer as well, like this. So it's something like this. Okay, and we are projecting it with the initial velocity u and at an angle of alpha from the inclined plane. Okay, so we are throwing a projectile with a velocity u at an angle of alpha from the inclined plane, and the inclined plane is itself at an angle of theta from the horizontal. So we are required to find the range. This will be the range. Okay, we want to find out the time of flight. Okay, so these are the two quantities that we will be calculating in this particular lecture, and in the next lecture I'll be telling you some more uh, 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 important quantity regarding projectile, which is the trajectory of the projectile. Okay, and then we'll delve deeper into projectile. So we want to find the time of flight, and we want to calculate range. Okay, so there are two approach to this problem, and I'll be taking the easier approach. Okay, so you can you can see that this on the face value does not look like a projectile, because if you see, we talked about a projectile motion which starts from the ground and the ball returns finally to the ground. Okay, but here it's totally different situation. You are throwing a ball up an inclined plane, or any projectile up an inclined plane. So the acceleration or the force of gravity is acting downwards. Now this acceleration will have two components. One of the component will be acting along the plane. Let us call this as gx, and another component of acceleration will be acting perpendicular to the plane. Let us call gy. Now in this projectile, there was no acceleration in the x direction. Okay, in the x direction there was no acceleration. There was acceleration only in the y direction, which was g. But in this projectile, if you see, if I compare it to this one, if I just turn it around like this, so it will become like this. Okay, now g is acting something like this, and we have one gy, another component gx. So there is acceleration in the x direction also, and this is basically the component of the total acceleration g, right? So this approach will be a bit difficult because I haven't told you about acceleration in the x direction. So I'll take a very easy approach, and that you can clearly see here. So this is the inclined plane, this is the projectile. Just for a moment, remove this plank, remove this inclined plane, whatever it is. Just imagine, the moment you remove this, it will appear like this. Okay, so there is a projectile which is at an angle of alpha plus theta from the ground. Okay, this was the inclined plane, and I have removed it. So there is simply, this is a question of projectile which has been projected at an angle of alpha plus theta from the horizontal. Very simple. And if this is the range, so I can break this range into two component. Look at this angle. If I take this angle ABC, so this AC will be r cos theta and this BC will be r sin theta. So I can say that this, for this projectile, this particular projectile, the x displacement is r cos theta and the y displacement is r sin theta. Yes, so this is a simple projectile at a velocity u whose x displacement is r cos theta, y displacement is r sin theta. Now I'll break this velocity into two components. The horizontal component will become u cos alpha plus theta and the vertical component will become u sin alpha plus theta. Okay, simple. These are the two components of the velocity. Okay, so let us assume that time of flight or time before hitting plane is capital T. Okay, it's not necessary that the projectile will complete the entire trajectory because it is hitting the inclined plane beforehand only, so the total time is T. So obviously you can say that the x displacement will be nothing but horizontal component of velocity into total time T, because again this is a simple projectile problem and there is no acceleration in the x direction, so this will be the x component. Okay, so I can replace this x with r cos theta. Okay, so this is the first equation that we have with us. This is the first equation. Now we'll talk about the vertical motion. We know that the vertical displacement is r sin theta. The vertical component of velocity is u sin alpha plus theta. Acceleration in the vertical direction is minus g. Time is obviously the same, capital T. Okay, and displacement is r sin theta. Now putting it in the kinematics equation, we know that S is equal to ut plus half at square. So for vertical motion, Sy is equal to uyt plus half ay into t square. Okay, so let's put it. R sin theta is equal to u sin alpha plus theta into capital T plus half minus g into capital T square. Okay, now let me put the value of time from the first equation that we have. If you remember, this is the first equation. So from here time becomes r cos theta upon u cos alpha plus theta. So let me put here. So I'll get r sin theta is equal to u sin alpha plus theta into r cos theta upon u I'm really sorry, u cos alpha plus theta, u cos alpha plus theta minus half g into r cos theta upon u cos alpha plus theta whole square. Okay, so one r will cancel out. Okay, this will be r square and it will become r. Okay, so rearranging this, I want to find r, so I am rearranging. You can clearly see after rearrangement you should get 2u square by g, in the denominator you will get cos square theta in the numerator you should get cos square alpha plus theta. Okay, and here you are getting you will get sine will be this will become tan alpha plus theta into cos theta